right, I want to talk about dilution. This is something that you're going to do more of. We already did dilution in the beginning of the semester, so you've seen the equation C1V1 equals C2V2 already. But let me see if I can make it so you can see those captions. There we go. Okay, so just in the example of like Kool-Aid, all right, we have a half a liter and we sprinkle some in, and of course it turns a pale pink color. We can actually measure the concentration of that at 0.280 moles per liter. Okay, so far so good. So if I add more drink mix in, because I like it more flavorful, we notice the concentration is increasing. We're adding more solute, so that makes sense. The concentration goes up. Okay, so say I like it nice and red, 4.05 molar solution. That's great. But my kids come along behind me and they don't like it as flavorful, so they dilute it. Can you tell me what happens if we dilute this by adding another half a liter? So we're going to use C1V1 equals C2V2. In this case, our initial concentration is what we're starting with here. We can use molarity as a concentration unit. And our initial volume is half a liter. We don't know what the final concentration will be, but we do know the final volume, if I add another half a liter, is going to be 1 liter. So the biggest mistake people make with this calculation is assigning the right variables to begin with. And I find that using this simulation helps to do that because it's a visualization of what you're doing. You can access it in the lecture notes if you go into presentation mode and click on the picture. And I think if you click on the picture and then copy the link, you can also access it that way, even not in presentation mode. Okay, so hopefully this is a good review for you. But what we're going to do is 4.05 times 0.5. Then divide that by the 1 liter to cancel out our units. And we're going to end up with molarity as our unit. Right? So C2 is equal to. By the way, if we have this in milliliters, we don't need to convert because the unit of volume cancels. As long as everything matches, you don't have to convert. So that means we're going to get molarity out of this calculation. And the answer is 2.025. It's half of what we started with because we've diluted it by double. All right, so let's see if we're right. Oops. Of course, it gets lighter in color because we're diluting, right? And our concentration is correct, okay? So I recommend that you play with this a little bit, and you can even use actual chemicals. Some of them are very pretty. Here's one of my favorites. It really does look like that. Very, very purple. All right, but you can play with dilutions using this simulation, and that's a good way to visualize what's happening. Okay. But remember that the important part is the equation is C1, or if you like CI, so initial concentration, V1 or I out there equals C final, V final. I usually write it like once, but the idea is the same thing. All right, you just need to make sure that your initials are together and your finals are together, and you know which one you're actually solving for. Another way to represent the same equation is to use molarities. So you may have seen this if you took high school chemistry in New York State, but you saw it written totally incorrect, by the way. Don't use this equation. You saw it written like this, and they gave you problems that always worked for this formula. I'm telling you now that it will lead you astray in college and your future work. All right, and so we want to be really clear that titration problems, which I'll show you an example of shortly, do not use this equation. This equation in every other state of the nation is used only for dilution calculations. Okay, so only when you're not reacting things. That's the big difference. You're just diluting it. In a titration reaction, you're actually reacting things. So we're going to do those calculations the same way we have been doing our stoichiometry problems.
But first, we're going to practice some more dimensional analysis and dilution calculations, right? So we'll do titration in a minute. So when I'm reading these, if I have a stock solution of 1 molar NaOH, I know that's going to be something important. So I'll just underline it. And I need 500 milliliters of 0.1 molar NaOH. So just a little context clue that I can use is this word of. Of always means multiply. It's a little trick. By the way, per means division. Difference means subtraction. And additionally, and means plus. Okay, so just some like math terms to watch out for in these problems. So when it says 500 milliliters of 0.1, that means these are going to go together. This will be one of my V's. Let's just call it V2. You could call it V1 as well. And this will be a C2 then, if I name it V2, right? So these match, they go together. The other one is by itself, right? So if I write this into my formula, we're going to go 1 molar times a concentration that I don't know because it's not listed here is going to equal the 500 mils. I'm running out of space. Times 0.1 molar. Okay, so that's actually, that goes up there. Okay, I rewrote it down here at the bottom where I had a little more space. So you're going to solve this by multiplying 0.1 times 500. None of those units actually cancel, but when you divide by, oh goodness, hold on. When you divide this by the 1.0 molar, we'll notice that the molarities will cancel and we're left with milliliters. Okay. So we end up calculating that there will be 50 milliliters for V1. All right, and so that makes sense. That has to be less than your final volume because you're adding water to dilute it. Okay, so second problem here. And again, you should be pausing and trying these on your own first and then come back to the video. We see the same kind of language. We have all of this much. So we'll go 25 milliliters of 1.5 molarity is going to make a solution that is 0.75 molar. And we need to find the final volume, right? So again, looking for some context clues to tell you which things are going to be multiplied together is the key to these problems. They're not mathematically that sophisticated, but you can get kind of turned around if you don't assign the variables together correctly. And so you go 25 times 1.5 divided by 0.75, and this time the molarities are going to cancel and you're going to get milliliters. You'll notice I didn't convert this to liters, so we don't need to do that because most of the time in lab we'll measure mils anyway. Okay, so dilutions, you don't need to use stoichiometry. You don't need to go through all those conversion factors. You could, you would still get to the same answer, but because you're not doing a chemical change, you don't have to, right? So we can kind of simplify the problems a little bit and just apply this equation. This is a figure from another textbook that I like. It's a graphical representation of all the ways that we have learned in the last 2 chapters to convert things. So in the beginning of chapter 3, we learn about going from grams of one thing into moles of that thing. So that's the red line, and you would use the molar mass, right? But you would use it so it's moles on top and however many grams on the bottom, right? And just to remind you, molar mass comes from the periodic table. The unit is always grams per mole, so you can flip it over in order to cancel grams and get to moles. When we were going the opposite direction from the moles of something into the grams, that's when you want to use molecular weight just as you find it when you calculate it on the periodic table, right? So that's going upward, this one's going downward. And so then, once we are in moles, we learned how to go from moles of substance A into moles of something else, right? And so it doesn't matter whether that's another reactant or another product. You can transfer between any two chemicals just by using the coefficients from a balanced equation. This is why we spent so much time learning to balance equations. Once you're there, then you can either figure out, this is the new stuff we just learned, you can either figure out how much volume that is equivalent to using the molarity. So remember, molarity is moles of B per liter of solution, right? So if you're going to be using the molarity, actually I put that in the wrong spot, I'm going to move it. So here we use the molarity as a conversion factor, and so when you're going from volume into moles, you're going to use the formula exactly as shown here. When you're going the opposite direction from moles into volume, you're going to flip it. So liters is on top and moles is on the bottom. And then finally over here, to go from moles of something into molarity, you just divide by the volume of solution, right? So we remember that moles per liter is this. You just literally divide by liters. You may need to convert that from milliliters or maybe even from grams using the density. All right, to go from here to moles, then you multiply by the number of liters, right? So they're like opposites. So this kind of graphic organizer can really help you to remember what you know how to do. It's a handy thing to have with you when you're working on your homework in your labs.